Here's a third example of topological spaces that are not Hausdorff. These spaces properly belong in real analysis. So for here, we'll motivate everything from calculus and leave the real analysis for the end. Now, if I have X space, T is our topology. It's going to be some collection of open sets satisfying the three conditions. We say X comma T is Hausdorff if and only if for any 2 points X and Y not equal in our space, there exist disjoint open sets U and V such that X is in U, Y is in V. So for any 2 distinct points, we can separate them points by disjoint open sets. Now, for example, let's recall how we do a Riemann integral. So we can assume f is continuous on the closed interval 0, 1. We want to find the area between our curve and the x-axis. So the way we do that, we form Riemann sums. So we'll take our interval 0, 1, we'll subdivide in smaller intervals, and then we'll fill in our curve with rectangles. And we use that to approximate the area. So for the formula, what do? We'll call the bases delta xi, okay, 1 for each rectangle. Then the heights are just going to be given by some point on our graph. So it's going to be an f evaluated at some xi in the interval. We multiply, we get the area of a rectangle, and then we sum over all rectangles. We take the limit as the bases go down to 0 in all possible ways. If this limit process exists and we get a number, we call that the Riemann integral, and we write it as follows. So we're interested in functions for which this limiting process exists. Now, theorem says it'll exist if f is continuous on a closed interval. Note, it'll also exist if we have f continuous except at finitely many points in the closed interval. Otherwise, we just call our function Riemann integrable. For our first pass, we're just going to let our space X be the set of continuous functions on the closed interval 0, 1. Now, if you haven't worked with function spaces before, it takes some getting used to. Here we have spaces whose points are functions. For the continuous functions in the closed interval from 0 to 1, we get to familiar territory by noting that we have a vector space. So if we take any 2 functions in here, take their sum, we get another continuous function. So closed under addition. If I take any function in here and multiply by a fixed real number, we get another continuous function. So closed under scalar multiplication. Then we'd have to show that everything's compatible, so we get a vector space structure. Note, we're not finite dimensional in this case. Next, for the topology, we have a metric space. So I'll define the distance between 2 points in our space, f and g, as the difference between f and g is functions. We take the absolute value, then we integrate over 0, 1. So we interpret this as we're taking, for our distance, the area between the graphs of our functions above 0, 1. Note, because we're using the absolute value, we don't worry about which function's on top. We just take the area of each piece. As an example, okay, in the graph here, the distance between f and g is just the shaded area. Now, we should show that we have a metric, so we have to show the 3 properties. First property, distance between any 2 points is greater than or equal to 0, and equal to 0 if the 2 points are equal. Now, if we take the difference between f and g, take the absolute value, that's a continuous function that's greater than or equal to 0. So, if we take the area under this function above 0, 1 on the x-axis, we're going to get an area which is always going to be greater than or equal to 0. So this holds. If we get exactly equal to 0, well, that means that the area under this function above the x-axis is equal to 0, So our function had to be precisely 0. That means f and g are equal. Then we have the symmetric property, which is straightforward. Finally, we have the triangle inequality, which follows from the triangle inequality for absolute value. So that'll still hold when we put functions in there. And then we can integrate term by term. So we'll still have a triangle inequality in this case. Now, because we have a metric, that says our space is Hausdorff, but the problem is it's not complete. So that's where the real analysis comes in. To show that our space is not complete, consider the following sequence of functions. So for a fixed n, I have f sub n evaluated x given by 0 on the interval from 0 to a half minus 1 over n, 1 on the interval from 1/2 to 1. For the other points, we just connect the dots. So we'll take values on this line here. Now, as n goes off to infinity, this point goes to a half. Our line's going to get steeper and steeper. And the pointwise limit, we go to this function here. Now, that function is not in our space. It's not continuous. But that's not enough to show not complete. So what I would have to do, show that we have a Cauchy sequence whose limit is not in our space. Now, we'll show that f sub n is a Cauchy sequence, and then we'll consider what its limit is. So let's take a look. Definition of a Cauchy sequence. Okay, our test is, someone gives us an epsilon greater than 0. We want to find a capital N such that if we let our indices go out past this capital N, the distance between f sub m and f sub n is less than epsilon. So the idea here would be, we're taking the area between our two functions, and we will get that less than epsilon. Now, for these type of functions, well, what's the area between two of these functions? Okay, if I sketch an f sub m and an f sub n, that's going to be the area of this sliver here. So, not too tough to reason out. As we let our capital N get larger and larger, these slivers are going to get thinner and thinner, and they'll be thin as I measure between any two f's that are far out. Now, suppose we have a continuous limit f for the Cauchy sequence. We'll show that f is equal to 0 on the interval from 0 to a half, equal to 1 on the interval from a half to 1. And the value at 1/2 is in play. But there's no way I could set the value of 1/2 to make this a continuous function. So there's no limit for the Cauchy sequence. That's a continuous function. Now to see this, we'll pick an a between 0 and a half for a Cauchy sequence. Okay, I'm going to assume that we're given an epsilon, and I can find some n such that the distance between f sub n and f is less than epsilon if we go out far enough. Now, we take the integral of the absolute value of f over the interval from 0 to a. Because we're on this interval, f sub n is equal to 0, so these are equal. Then, because these are positive functions, I can expand our interval of integration to 0, 1, and use an inequality here. Now, this is just the distance between f sub n and f, so that's less than epsilon. That means, okay, note, there's no n in this expression here. So we have this integral less than epsilon for all epsilon greater than 0. That means that this integral is equal to 0. Because the a is arbitrary, that means our function is going to be equal to 0 on the interval from 0 to a. A is arbitrary and less than a half. So we get our function equal to 0 in the interval from 0 to a half. A similar argument gives our function equal to 1 on the other interval. So the only thing we don't know is what's happening at the point 1/2. Now, the choice of the previous example so that I couldn't get a continuous function by fixing at one point. That forces us to look at the space of continuous functions on the interval with a finite number of discontinuities. Now, even this space is not enough to get our complete metric space. Now, rather than go through the Cauchy sequences again, let's just consider certain pointwise limit. So going to set up a sequence of functions. Okay, I'm going to start with this set of rational numbers in our interval. I'm going to enumerate them, so I'll just list them as a sequence, a sub I. And I'm going to call the subset of a sub n, as a1 through a sub n. Then I'm going to define f sub n of x equal to 1 on a sub n and 0 elsewhere. Note, this is going to be 0 with a finite number of discontinuities, so it's in our space. If we take the pointwise limit, what's happening? Well, we're just adding in more and more points that have value 1. So this limit is going to be equal to 1 on the set of rational numbers in 0, 1, and 0 on the irrationals. Now, problem here, this function is not Riemann integrable. So if we consider Riemann sums, so we approximate the area using rectangles. If we use rectangles that are always above our graph, these Riemann sums always have value 1. If we use lower Riemann sums, so ones where we have our rectangles below the graph, okay, they're always going to be at height 0. So these Riemann sums are going to have value 0. Since these are never going to be equal, we don't have a Riemann integrable function. That limit doesn't exist. Let's recall what we have. Start with the continuous functions on the interval 0, 1. This was a Hausdorff space. It was a metric space, but it wasn't complete. We found a Cauchy sequence whose limit was not a continuous function. The limit was Riemann integrable, though. That led us to consider continuous functions on the interval, possibly finitely many discontinuities. This was worse. We're able to find a sequence of functions here whose limit was not only not in the space, but which was not even Riemann integrable. So what now? Well, that answer comes from your real analysis course. So here we'll just give an outline. What we have here is Lebesgue integration. This is going to generalize our usual integral. The idea is, for our Riemann sums, we were using rectangles to approximate area. With Lebesgue integration, we're still going to use something like a rectangle. The heights are fine, but we want to change what type of bases we use. That's all we'll say about that here. Now, the consequences will be, if we have a function that's Riemann integrable, then it'll be Lebesgue integrable. In that case, the two integrals will be equal. So this is the generalization that we're looking for. Next, we're able to correct our integrals by changing our function on a set of measure 0. Again, I won't say what measure 0 is here. For us, it'll be enough to note countable subsets will have measure 0. So for this function here, okay, it's not Riemann integrable, but we could change these values of 1 on the rationals to 0, and then our Riemann integral, which will be equal to the Lebesgue integral, will be equal to 0. So that's going to fix the integral that's not working here. Now, how about a topological space? So what we would do is, we consider all functions on 0, 1. Okay, we're going to consider functions that have this property of being measurable and such that their Lebesgue integral, okay, is finite. Now, this space here is not going to be good enough because the problem is, well, we'll have a lot of functions that are going to have distance from 0 equal to 0. So we're going to form a quotient space here. We're going to mod out by the relation f is equivalent to g if and only if f and g are equal on a set of measure 0. Once we mod out by this relation, that fixes everything. So the space L1 is going to be a Hausdorff space. It's going to be a complete metric space. Okay, and we're going to use the same metric that we had before. The only catch, the points are not going to be functions, they're going to be equivalence classes of functions.